Hi, I'm Victor Costa from University of Coimbra, and I will present to you the paper using skill rating as fitness on the evolution of GANs. So I will start with a brief introduction about generative adversarial networks. GANs are an adversarial model that uses two neural networks trained as adversaries. The generator has the objective to fool the discriminator, and the discriminator has to distinguish between samples from the generator and from an input dataset. After the training, the generator is able to produce innovative samples resembling the input dataset used in the training of the discriminator. There are two examples. In the left, a digits dataset, and in the right, a faces dataset. However, the training of GANs is hard, and is frequently affected by some problems. The first problem is the vanishing gradient that occurs when the discriminator becomes too strong and it stops the generator to improve. And this makes affect the equilibrium of the GAN training and impact the convergence. Another problem is the mood collapse problem. This problem occurs when the generator captures only a small fraction of the input dataset. So here we can see three examples of this problem happening. So we proposed earlier COEGAN, that is a method that designed the GAN model as a competitive coevolution method. So our model takes use of competitive characteristics in GANs to apply a coevolution and a neuroevolution approach. The objective is to solve those stability issues I presented earlier and provide the automatic design of neural networks. For this, we use two subpopulations of generators and discriminators and evolve them using a neuroevolution approach. In our method, the genotype is composed of a sequence of genes representing layers in a neural network. We can see here two examples of the genotype of a discriminator and a generator. To evolve the individuals, we use three mutation operators. These mutation operators can modify the architecture of individuals, adding, changing, or removing layers in the genotype. To evaluate individuals for discriminators, we use the loss function of the original GAN proposal that is given by this equation. And for the generator, we select the FID score to represent the fitness function. So this score uses a trained inception network that is previously trained on the ImageNet dataset. And this network is used to compute the difference between the distribution of samples created by the generator and samples from the input dataset. So in this work, we propose the use of the skill rating as fitness instead of the fitness I presented earlier in the previous slide. Our main motivation is to have a self-contained solution without the need of an external component like the FID score. Furthermore, the skill rating has a lower execution cost when compared to the FID score. So in our proposal, each pairing between generators and discriminators are considered as a game and is used to calculate the skill rating using the Glyco2 game rating system. The rating system is capable of quantifying the skill of players through time, adjusting the skill according to the skill of the adversaries. So to evaluate our proposal, we compare the COEGAN method with the skill rating, COEGAN with our previous fitness proposal that is basically dependent on the FID score, a non-evolutionary approach based on GAN, and also a random search approach. In this random search approach, we use basically the same algorithm in COEGAN, but we replace the fitness with a random function. It's a uniform random distribution, and we keep the same parameters from COEGAN For the DCGAN, we use a non-evolutionary approach based on the DCGAN architecture. So we execute our experiments in the MNIST dataset and in the SVHN dataset. In this case, we perform COEGAN for 50 generations with a population of 10 individuals in each population of generators and discriminators. As first results, we show here the FIG score for the 4 solutions evaluated in our experiments. We can see that our proposal with the skill rating performed better than the random search approach. However, the COEGAN and the FIG fitness is still better than the others. Here we show the relation between the FIG score and the skill rating in executions guided by the FIG and the skill rating. We show that there is a correlation between the FIG score and the skill rating, indicating that the information provided by our proposal, that is the use of skill rating as fitness, is relevant to our approach. In this graph, we show that the average number of parameters in the networks of the individuals in our proposal is more efficient than when compared to DCGAN. Note that the DCGAN is constant because it didn't use an evolutionary approach in the solution. Here we present some samples created by the 2 approaches, COEGAN with FIG and our proposal in this work, that is COEGAN with the skill rating. We can see that both solutions were able to capture a good representation of the SVHN dataset. We also did some experiments with the MNIST dataset. We show here that there is a more clear relation between the FIG score and the skill rating, confirming our hypothesis that the skill rating is useful to guide the evolution of GANs in our proposals. We also show here the behavior of the FIG score, comparing our 4 solutions when training with the MNIST dataset. And in this case, also in this case, COEGAN with the skill rating is better than the random search approach. But the COEGAN with the FIG score is still better than others. So to conclude, we found that although the FIG score as fitness provide better results, the skill rating also contribute with useful information in the evolution of GANs. The experiments also evidenced that the use of skill rating is better than the random search approach, and replacing the feed by skill rating avoid the use of an external costly component in the solution. And there is also a correlation between the skill rating and the FIG score that is more visible in the MNIST dataset than in the experiments with the SVHN dataset. As future work, we pretend to improve the strategy to obtain the results of matches between generators and discriminators when feeding the skill rating system. We can also take into account individuals from previous generations on the calculation of the skill rating, and finally bring information about the variability of samples produced by generators to approximate the information provided by the FIG score. So that's it. Thank you for listening.